Howdy, howdy, howdy.
Hello. How's it going?
Good, I think.
It's almost lunchtime.
Yeah, it's always difficult. It's lunch. Oh, William.
Oh, Kruger,
So I have a question to ask you.
what is it?
Do you know who our math teacher, Mrs. Meyer, is? She used to be Ms. Hamilton. Then she got married, and now she's called Mrs. Meyer.
I've never had her, but I've heard of her.
Okay. I'm going to give her your name. She's working on her master's degree, and she wants to interview some people. Would you mind being interviewed by her?
I would not. No, that'd be great.
Okay. All right. I will do that then. Okay.
Sounds good.
Somebody gave me your name and knew that you were in my class, and so it was an easy thing for me to do, and I'm very proud that I remembered. What's you're looking for? What's for lunch? Chicken Alfredo pasta.
Hello, Raina.
You guys look so different without your masks. You know that? Tomorrow we get to see each other without our masks. You get to see me without my mask. Karina.
I was too worried about what's for lunch.
Mr. Kruger,
Yes.
why did you take that test grade out of school?
I don't understand your question.
Like the grade for the first test you took is like no longer in Soji.
I know it's exactly.
Oh, it is, huh?
What it is.
On everybody's?
I don't
All right. I must have unpublished it by accident.
Yeah.
A lot of things happen that I don't realize happen.
Yeah, because all of a sudden I had like 104% in this class. So that was like something
I know
doesn't
it.
Yeah, and I'm looking, and that's not what I'm seeing on my end. Wow.
I know I got
I wonder how I did that.
I think Schoolgy's just bugging. No, I'm saying Schoolgy always is nice.
If I told you guys have a,
Oh yeah, you did finish.
your teacher isn't the smartest guy in the world. Raina, I will fix that, okay? But thank you for telling me. Why that happened, I don't know, okay? Grayson, you want to get the door? All righty, give me a holler. Raina's here. Zach Brandenburg, are you here? Where are my Zoom people? Zach? Oh. Zach is here. Zach, I was just giving you a holler. So Zach is here. Alexis, are you here?
Here.
Caleb? Sarah? Sarah? All right, Sarah. Gabe? Where's Gabe? Right here. Gabe. Lily? Groover? Tucker is here. Grayson is here. Karina, I already saw. Gibbs.
Yeah, I'm here.
Okay. Ella.
Here.
Bill, William, I already talked to. Sorry, William, I almost called you the wrong name. Bailey.
Here.
Sophia.
Here.
Jaden? What's that? And why do you have that open?
Lily said that she was having problems with her laptop.
Got her in right now. Will you put your computer away, please? Okay. So who was I at? Jaden, are you here? Yeah, he's here now. Okay, Jaden's here. Jaden. Morgan,
Here.
Jordan Smith,
Here.
Audrey,
Here.
Hope.
Here.
Alrighty. So I'm just missing one person. Yeah.
So this is supposed to be on Wednesday next week,
Yep.
but we only have 55-minute classes on Wednesday.
I'll have to make a 55-minute test. Or you get as much done, or I give you another 2-hour test and you try to get it done in 55 minutes. It doesn't matter, it's curved, right?
Oh, that's true.
Right?
So you only
Still
get,
matters.
hopefully there's not this one speeding person that can get.
I understand that. Okay. So I had this conversation with my wife when I saw the schedule, because it's a valid schedule. For me to be flippant that way is not very nice, and I apologize for that. So I was talking to my wife about this, and I said, you know what? I'm going to write a 55-minute because if everything's normal on AP, okay, you have 4 tests. One's a half hour, one's 42 or 45 minutes, and one's an hour. Okay. And so to give you one that's 55 or just bleeds over 55 is very reasonable, and that's what I will do. Okay. Right now, tomorrow I'm just going over the quiz, pretty much. There may be a little bit of the notes in class that I might go over. It kind of depends how many people have questions and that type of stuff. But if we're on track on a Wednesday, I will adjust my test to be about 55 minutes. Okay. But you gotta understand, it might be a tad over 55 minutes, but that's what the curve is supposed. The curve is supposed to fix my mistakes, if you understand. Okay. So, has everybody got that? God, it's just so cool seeing everybody. Alrighty. I am going to go over some notes, and I'm going to go over the squeeze theorem, which is on 1-3. And you're going to be given some problems to do on those, and I will put those problems in on the 1-4 assignment. Remember, I removed them from the 1-3 assignment, I believe. Okay? And so you'll see those changes coming up. Plus, I'm going to have a handout here that I'm going to hand out when I'm done with these notes about the 1-4, and that will be due Friday. And so you will see that attached to an assignment of BISTERS. Everybody have that? Okay, I'm going to update my attendance. I used to never do attendance right away, but I do it now because I'll forget to do it. Okay, that's what you're gonna look forward to. So, Tucker, good question. Okay. All right, let's see if I could share my screen. So you guys can see my screen. It says the squeeze theorem right here.
Yeah.
Okay. So I want to do one thing here. Come on. All righty. So I'm going to have a bunch of different colors. So the squeeze, and I might have already started this. The squeeze theorem says this. If you have three functions, if f of x is less than or equal to g of x, which is less than or equal to h of x. So what it's saying here, remember f, g, and h give you y values, correct? And so this graph will be above this graph, which will be above that graph. Okay, and I'm going to give you an example in a second. And the limit as x approaches c of f equals the limit as x approaches c of h, and that's equal to some number that I'm going to call L. I know that to be true. So the functions are in this order, and at a particular c, both f and h has a limit that I call L. Then what has to happen for sure is the limit as x approaches c of g of x, that has to also equal L. So we use the squeeze theorem to find limits of functions in which we can't substitute, we can't factor, we can't multiply by the conjugate, and we can't rewrite the fraction somehow. Okay, so we can substitute. There's just no way we can do that. And so I'm going to give you a function, two functions. I'm going to call one of my functions f of x. I'm going to say that's the cosine of x. So if you remember, cosine kind of looks like this. It has peaks and valleys, right? And the highest ratio you can get from cosine is 1, and the lowest ratio you can get is a -1, okay? So right here, there's a nice horizontal function that I'm going to use, that I'm going to call h of x, and that's going to equal 1. So this is 1, or this is h of x, and this is f of x. So h of x is always bigger than f of x. They're only the same at x equals 0, correct? And then I'm going to have another function, and this function is g of x. And g of x is going to be the sine of x over x. Now, why am I choosing that? I want to prove that the limit as x approaches 0 of the sine of x over x is equal to 1. And this is one of those functions I cannot simplify and substitute. And we really only have two methods to find out what that limit is. And one of these methods, Christmas. One of these methods is using the squeeze theorem. And if I graph this sine of x, it looks like this as it approaches 0. It's in between there. So here's g. It's being squeezed by f and h, correct? So my proof, once I know this, once I know that this is true from this graph, here's f, here's g, here's h, here's the y's for h, here's the y's for g, here's the y's for f, and that g is in between h and f. And guess what? The limit as x approaches 0 of the cosine of x happens to be what, Alexis Carlson?
1.
1, because the cosine of 0 is 1. And the limit, so that's my bottom one, the limit as x approaches 0 of 1, right? That's my top function, right? This is f of x. This is h of x. Audrey is what?
1.
1 also. Therefore, and this is how math people write the word therefore. Do you guys know this? Because math people can't spell the word there or for, and imagine what it'd be like if you combined them. So they use these 3 dots. Therefore, the limit as x approaches 0 of the sine of x over x must be equal to what number, Audrey?
1.
1, because these two are. End of proof. Q, E, D. This question right here and this question you'll see quite often on multiple choice questions on the AP exam. And the problem is right now it's September and the exam is in May. So somehow in your notes, when we start studying, you're going to have to write down like important, make sure I know this. Know this. You don't have to be able to know the proof. You just have to know that this particular function as x goes to 0 is 1. Okay. This you're going to see on the next quiz. This proof. Prove that the limit as x goes to 0 of 1 minus the cosine of x over x equals 0. So this is how we're going to start this proof. We're first going to multiply this by something. And what we're going to multiply it by is the conjugate. Bailey, what's the conjugate of 1 minus cosine x?
1 plus cosine x.
1 plus cosine x. Perfect. So I'm going to multiply the top and bottom by 1 plus cosine x. And you're going to see why in a second, okay? So this denominator now is going to become x times 1 plus cosine x. Bailey, what do I get when I multiply 1 minus cosine x times 1 plus cosine x?
One.
Can I assist?
Yes.
Okay. 1 times cosine x is what?
Cosine x.
A negative cosine x times 1 is what?
Negative cosine x.
What's cosine x plus a negative cosine x?
0.
0. So then what is minus cosine x? So I don't have a middle term, correct? Okay.
Correct.
So what's a minus cosine x times a positive cosine x? It's going to be a minus what? What's cosine times cosine? Pardon?
Cosine x squared.
Yeah. Cosine squared x. Would everybody agree? Caleb, Gabe. See, for some reason, the names Caleb and Gabe are like the same name, even though I know they're not. Okay? And your hats are always so cool. But you guys don't look anything alike, but I just not getting it figured out. Okay? It's not you, it's me. So Gabe, do you remember trig identities? Okay. Mr. Karsh taught trig identities. He taught you guys trig. And actually, I'm going to have to tell Mr. Karsh I'm pretty pleased because you guys had like, you know, in March, everything went to HE double toothpicks, didn't it? And you guys know your stuff pretty good. I'm actually pretty impressed with this class. Now, Gabe, in calc, you only need to know 2 trig identities. This is going to be one of them. It's my favorite, absolute all-time favorite, okay? And I'm going to show you why. And then you're going to tell me what it is, okay? I'm going to go to the unit circle. I'm going to throw in a little right triangle here. Here's 1, correct? This point right here is x comma y, correct? That means this thing here is x, this thing here is y, and it means the Pythagorean theorem means that's x squared plus y squared equals 1, right? A squared plus b squared equals c squared, right? And what's nice about c, it's 1, and 1 times 1 is 1. You can't get an easier problem than 1 times 1. I don't think. Well, 0 times 1. 0. So that's not trig, is it? But it gives me an identity. Do you know what the identity is? You're jumping way ahead. I'm talking about here, and then we'll come here because yes, you are correct, but you think faster than I can talk. Okay? So what's x squared? I want to make this into a trig identity. Or cosine squared theta, right? Plus, yeah, equals 1. That's my favorite. So sometimes I get hints about what's on the test. I said, make sure you know my favorite identity. It's that one. Because all I need to know is the Pythagorean theorem. I am terrible about memorizing. I'm good at building stuff on math. Does everybody understand that? I just build. Boop, 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 boop. Well, I need to know the Pythagorean theorem. I need to have a few basics, right? All right, so back to Gabe. I can transform this in this 1 minus cosine squared into what? Sine squared x. Karina, are you following that? Karina?
Sorry, I thought I was on mute.
You were on mute.
Yeah, I'm following it.
Okay. This thing's a fraction, right?
Mm-hmm.
Okay. Dealing with operations of fractions, which you must have learned maybe 6th grade. I loved multiplying fractions because you could multiply straight across. And in calculus, this is a fraction that was caused by multiplying straight across. Okay. In fact, I can say this is the sine of x over x times the sine of x, because that's what sine squared x means, over 1 plus the cosine of x, right? You just multiply straight across. That was the easiest thing to do in fractions. 1/2 times 2/3, 1/3. Now, I'm taking a limit, correct?
Mm-hmm.
Remember the quiz we took yesterday? The very last question was on some properties of limits. It said, if you have two functions, right, you got a function here times a function here, you can take the product of its limits. Correct?
Mm-hmm.
So I'm going to take the limit as x approaches 0 of the sine of x over x. That's one function times the limit as x approaches 0 of the sine of x over 1 plus the cosine of x. Correct?
Mm-hmm.
Do I know the limit of that? Karina?
Yes, it's 1.
It's 1. Boom! Right? So I'm going to replace that with 1. Do I know, can I substitute 0 into the denominator? Well, what's the cosine of 0?
1,
1. What's 1 plus 1?
2, so you
Oh.
can do it.
So I can do it, right? Because I got 2 on the bottom, right?
Mm-hmm.
So what's the sine of 0? The cosine of 0 is 1, right? The
Mm-hmm.
sine of 0 is what?
0.
0. So look at all this complicated math. If you would show this to any elementary school kid, my guess if you show it to any teacher in here that's not a math teacher, they would go, oh my gosh, that's gibberish. But I bet you anybody can do that problem. Do you see how easy that got, Karina?
Mm-hmm.
What is 1 times 0 divided by 2?
0.
0. And that's the end of my proof. Okay, doke, folks. You got those in your notes? You're going to need them for the quiz. Very good, Karina. So we're going to do, these are some of the examples that you're going to do on your homework assignment. And these are the kind of problems that are on the AP exam. And if you take a look, again, these are trig limits. And you can only use these two to help you out. So Grayson, this sine, this is cosine, this is tangent. Is there a relationship between tangent and sine or cosine or both? Yeah, so tangent is sine x over cosine x all over x. Would you agree with that? Okay. Oh yeah, you have to. You're the one who told me. Okay. So this is the same as the sine of x over cosine of x times what number? Or what thing? 1 over x. Again, I got two fractions that I'm multiplying, correct? And I can multiply straight across. And I get the sine of x over x times the cosine of x, correct? Which is equal to the sine of x over x times 1 over the cosine of x. Would you agree? Oh, I know this one. And I think I know this one. Correct? So it's limit time. The limit as x goes to 0 of the sine of x over x times 1 over the cosine of x. Grayson, what's this? Can I substitute, will I have division by 0 if I plug 0 into x here? He says no, because the cosine of 0 is 1. So I have times 1 over 1. Would you agree? Again, a math problem that all the teachers in the school should know. Correct? And that answer is 1. Perfect. All right. Now, to apply this rule, what has to be true is this in here has to be identical. Okay? Now, I'm going to bring out my voodoo stamp. I'm going to show you some voodooism. Okay? And I will hammer you, Gibbs, if you do this. Are you listening to me?
Yeah, I got you.
Okay, so this is what my voodoo stamp looks like. Okay?
Yeah, no, I
This is
saw
what-
it on my last test.
Did you get one on your last test?
Oh, yes, I sure did.
Oh, I used to have people that tried to collect them. There is a guy, Robert, what was Robert's last name? Robert Cooley. What he would do, he was really smart, but he would tell people voodoo stuff, and then people would actually write it on their tests, and then I'd stamp it, and he'd start laughing. Gibbs, if I give you, did you cry when you got a voodoo stamp?
Nah, I didn't.
You made it through, right?
Just a little disappointed in myself.
Yeah, well, I get disappointed myself. I mean, when I run the copier and I can't copy stuff, I go, poop. What I mean, I feel obligated to get rid of the voodooism. Okay, so this is a voodooism. The limit as x approaches 0 of the sine of 4x over x. This is what students will do. They get their magic and they go this, bam. And then they say the answer is 4. And 4 is the answer. And I give them no credit. I don't even give them a 10th. Even though the answer is correct. Because I don't care about the answer. I care that you do correct math. This really has parentheses around it. This is an angle measure that gets changed to a ratio by sine. You cannot do this. This is how you have to do this. I need to make this a 4x. Why? Because there's a 4x in here, and these two need to be identical to get the limit to be 1. So I am going to multiply this by 4, but what I'm going to do here is multiply out here by a scalar that's identical to this, because now I got 4 over 4. Does everybody follow that? So the limit, the answer to this is the limit of this is 1. This right here is 1. 4 times that limit gives me 4. That's the work I need to see. Okay, Gibbs?
Yeah.
Okay. So Gibbs, I'm going to give you one down here. You ready?
Sure.
My guess is you already know the answer.
Mm-hmm.
What am I going to multiply this bottom by?
5.
What am I going to multiply the outside limit by?
1.
What?
Oh, 5 again. Okay.
5, right? Because 5 divided by 5 is 1.
Mm-hmm. Yeah, I get
So
that.
now you're going to write 5 times the numerical limit you get for this, which is 1, and then you get 5 for an answer. Okay?
Yep.
Ella, Nelson,
Yeah.
okay? I got a 5 up here. Ooh, poop. Even though I like a 3, it's not a 5, is it?
No.
What can I multiply 3 by? Multiply now. What can I multiply 3 by to make it a 5?
Can I pass?
You sure can. Then I'm going to pick Raina Berry. What can I multiply 3 by to make it 5? It's a fraction. Yes, it's 1 2/3, but I very rarely in math use a mixed number. I almost all the time use an improper fraction. 5/3. Does that make sense, Ella? That's 5/3?
Yeah.
Okay, so it's going to be 5/3 here. Right? Because this is going to happen here, right? Ella?
Yep.
Okay, so this is going to be 5/3 times what number?
1.
1, and you get 5/3 as your answer. Okie doke, Ella?
Yep.
All right. Hope, this is how I'm going to do this one. I'm going to rewrite x over the sine of x. Hope, do you have an idea of what the limit of that is?
No.
Okay. So what I'm going to do here is I'm going to multiply the top by 1 over x and the bottom by 1 over x. So Hope, what is x times 1 over x?
X over X. 1.
Yeah, it's 1. Perfect. And down here, I'm going to have the sine of x over x. Okay?
Yeah.
So now I'm going to write the limit as x approaches 0 of 1 over the sine of x over x. So I got division, and what I can do is I can take the limits of each of these separately. What's the limit as x approaches 0 of 1? Hope.
1.
Perfect. Over, what's the limit as x approaches 0 of the sine of x over x? Look right up here.
1.
1. What's 1 divided by 1?
1.
There's your final answer. All right, Caleb? All right, Hope?
Yes.
Okay, now we're going to jump to the 1.4. Nope. So, Jaden, how are you doing?
Doing good.
So, Jaden, so we're going to talk about continuity. And what I'm going to do is I'm going to hand out the packet to the 5 individuals that are here. And then I'm going to have the packet online today, but it's not going to be due till Friday. It'll be due as an assignment and it'll be attached. Does everybody understand that? Jaden, do you understand that?
Yep.
Okay.
Yes, I do.
We didn't get them yet?
Also, I forgot to turn in my homework yesterday, so I submitted pictures.
Online?
Yeah.
Yesterday? So this packet has to deal with something called the intermediate value theorem, which we're going to talk about later this period. But when you see the packet, if you look at it, there's a lot of information. The work that you do isn't till you get to the very, very back that says problems. And I'm going to go through this on Thursday. Does everybody understand that? And then you have 2 problems that will need to be done to be handed in. So that's all I need is that part right there. Okay? Jordan Smith, does that make sense?
Yes.
All righty. So let's take a look at continuity. What does it mean for something to be continuous? And anytime I do work, this is what I think. That continuous means I have a graph that I can draw a curve without lifting a pen or a pencil, and that it's uninterrupted. But I can never say that as a justification, Caleb, ever, because they won't accept it. That's not mathematical. I have to say this: a function is continuous at a point C if 3 things occur. That f of c is defined, that the limit at c exists, and that limit is equal to f of c. Okay? Those 3 things have to be true to have something continuous at c. I'm going to give you 3 examples of something that's not continuous at c. So I'm going to call this c. I'm going to draw this thing here. And I'm going to have a little mark right here. This is F. Jordan, what is this?
That is a whole.
That is a hole. What is that telling you?
That at f of c, there is not a point that it is defined.
So it does not exist, correct?
Correct.
Okay, perfect. You're doing wonderful. Can I keep asking you questions?
Fire away.
All right. What's this? It's a y value, right? How should I label it? I can't call it f of c because it doesn't exist.
Right.
Is
That
it?
would that be f of x?
Yes and no. I'm going to call it this. Do you know why?
Because that's what the limit of f of c would equal.
How do I know it's the limit as x approaches c of f of x, correct?
Correct.
So the limit exists, right?
Yes.
How do I know that?
As both sides are approaching f of x, it approaches the same point.
Right. So as I approach c from both the left and the right, then these y values approach that L, correct?
Yes.
This is a kind of a poor drawing, but I think you get the idea, right?
Yep.
So this is an example of something not continuous at C. There's a limit, but there's no f of c. Does that sound correct?
Yes.
All right. So let's draw this one. Lily, still got a hole?
Yeah.
Okay. What should I call this? Right here. Lily.
Would that be L?
No, it's not L, but it's a nice try. You want to try again? I'm going to tell you L is down here. Does that make sense why with my fancy drawings?
Yeah, I know the L is right there. I just have no clue what's on the other.
Okay, that's fine. We can ask Morgan Schreifels. What do you think, Morgan?
Would that be F of or FC?
Yeah, F of C. Perfect. So F of C exists. Would you agree? Morgan, would you agree?
Yes, sorry.
Okay. And the limit exists, right? The limit as x approaches C of f of x is equal to L, correct?
Correct.
Why is it discontinuous, Sarah Gamma?
I'll pass.
Okay. Sophia, why do you think it's discontinuous? Right, it's discontinuous, correct? I mean, there's no way I can draw this without lifting my pen, right?
Yeah. I think that it's because the hole and where f of c exists isn't at the same spot. Or
Right,
the limit is different than f of c.
right. So it's this part right here. Would you agree? This is
Yeah.
not true. So the limit as x approaches c of f of x does not equal f of c. Those y values aren't the same. Okay, would you agree, Sophia?
Yes.
Sophia, that's kind of a cool picture. All right, so here's C. Here's F. Tucker, what's this line? No. It's F of C, isn't it? Because it's where it's defined, right? Okay. So Tucker, you would also say that is not continuous, correct? It's my third and final drawing. Why?
There's a jump in the graph, so the limit one is approaching from the right of C. Limit x approaches C from the right. This equals does not equal the limit is x approaches C from the left.
So that does not exist, correct?
Yeah.
And we call that a jump, but this is how we justify it mathematically, correct? Okay. Does that make sense to everybody? So these three things have to be true. F of C is defined, which it is here and it is here. The limit has to exist, which is true in these two, but not here. And lastly, the thing that ties it all together is that limit has to equal the y that you get when you plug in c. Everybody with me on that? All right, we call these two, this one and this one, these two on the left and the far right, removable continuity, or excuse me, yeah, removable discontinuity. Because if they both have limits, has a limit. This one has a limit. What it needs to have the limit be defined at f of c, and then it would be removed. In other words, if I simply filled in this point or moved this point down to here, then everything would be okie dokie, correct? All removable discontinuity have limits. So you must remember, two things have limits: continuous functions and functions with holes. I'll say it again. Two types of functions have limits: continuous limits and limits with holes. This one is non-removable. I can't color that in because then I wouldn't have a function. Okay, this jump is here. So this has no limit. And since it has no limit, it's called a non-removable discontinuity. Okay, so we're going to take a look at functions with one-sided limits. We kind of talked about this function before. F of x equals the square root of x. It looks like this. Its domain goes from 0 to positive infinity. Oh, I guess I wanted this. Its range goes from 0 to positive infinity. So it would have a limit as x approaches 0 from the right of f of x, it would equal 0. So it has a endpoint that has a right-handed limit. This looks like this. If I say its domain or its input values are only negative numbers or 0. Its range still goes from 0 to positive infinity. So like I'm inputting here a -4, and it tells you the first thing to do in here, give me the opposite sign of that -4, or multiply that -4 by a -1, and you get 4, and the square root of 4 is 2. So I would have the limit as x approaches 0 from the left of f of x, and that would also equal 0. Not too bad? William, not too bad?
Not too bad.
Okay. Alrighty, so we're talking about step functions. Probably the one that's taught the most is this one, which is the greatest integer function. And I remember learning this. This is also another symbol for greatest integer. I think this is the way the book does it. I think this is the way you guys learned it from Mr. Karsh. So if I had something like this, what's the greatest integer I can have that will not exceed 2.1? Well, that'd be 2. And I remember seeing this when I was a senior in high school, and I go, oh, I can do that. I just dropping off the decimal. And I said, give them to me, Mr. Eckstein. Because Mr. Eckstein was my teacher. He gave me 7.5. Now I can do that. That's going to be 7. Right, William?
Yeah.
Okay. And then Mr. Eckstein did this. And I said a -2. And he says, no, it can't be a -2. Why can't it be a -2?
Because that's greater than.
Yeah, it's bigger than -2.1, right? Right?
Yeah.
So this has to be what? What's the biggest integer without exceeding a -2.1?
-3.
-3. So if I take a look at the graph of this, here I am from here I am from -3. Obviously, if I stuck a -3 in there, it'd be a -3. But here's a -2 point whatever. And so at a -2, it would jump up to here. And it looks like this. Would you agree with that, William?
Yeah. Just a quick thing. So I thought that when the little prongs were on the top, you were supposed to round up, not down.
No,
But okay, so that's not right.
correct.
Okay.
And I've never heard them called prongs, but I'll use that. Can I steal that from you?
Yeah, you can.
I kind of exaggerated my prongs here. Sorry, they should have been more subdued like this.
All right.
Okay, now, William, the problem with this is for me, I thought it was a function that was kind of rare. And it's actually a function that we use quite a bit. Let me give you an example. I invest my money. I for sure put my money in a bank and I get interest. And so let's say I stick $100 in here and it stays there for a month. And then when on the first of the month is when I get my interest applies, it'll go up, correct?
Yeah.
And then it'll stay there till I figure out interest again, and then it'll go up, correct?
Yep.
So this is interest. Then I thought, oh, because you know what I would do on the 15th of every month when I was 9 till I was 22 with my dad's shop? You would have no idea, you weren't there. I would help load steel into my dad's shop because that was his inventory. He made stuff out of steel. So I was thinking about that the other day. I remember unloading that steel. So let's say this is the beginning of the month. And by the end of the month, the steel has been depleted, correct?
Mhm.
And then what do I have to do? I have to order some more steel. And if it gets depleted at a constant rate, which I don't know if it's true or not, this is just a model of a situation. I'd have a step function that would have oblique segments, wouldn't I? Limit, left endpoint, limits in the middle, no limit on the right. Limit on the endpoint, no limit on the right. Limit on the left, no limit on the right, correct? So when is there an existence of a limit? Well, normally we say the limit from the left has to equal the limit from the right. But we can have limits that go left or right. Now, how much time do I have here? I have a few more minutes. I'm going to skip this and come back to this stuff right here. Okay, I want to talk about the intermediate value theorem. So the intermediate value theorem says this: if I have a function, if f is continuous, Zach Brandenburg, are you a science fiction person?
Not really.
Not really. Okay. Do you read?
Yeah.
What kind of books do you read? Zach.
Picture books.
Picture books, like cartoons or what?
What?
What picture book are you reading right now?
None at the moment.
None at the moment. Okay. Are you taking a language arts class?
Not right now.
Okay. Besides Calc, what are your other classes?
Chemistry, German, US history.
Oh, you're an A-push. Okay. You got a lot of reading in there if you're taking A-push. So F is continuous. How do I want to write this? I want to make sure I get it right. If F is continuous and K is, how do I want to write that? Give me a second, Brandon, and then I'll ask you my question. I'm gonna write it this way. Oh, this is why I started wrong. If F is continuous in the interval A, B, and there is a K where F of A is less than or equal to K is less than or equal to F of B, then there exists a C in AB where F of C equals K. All right, you ready, Brandon? Here are my questions. What kind of value is K? Is it an X value or a Y value?
It would be a Y value, right?
Yeah, how do you know that?
Because it's listed, it says it's greater than F of A and less than F of B.
Yeah,
And
the purpose of F is to give you what?
Y value.
Y value, perfect. And so what's C then? A Y value or an X value?
An X value.
How do you know that?
Because it says F of C equals K. And
You're doing really well.
If there's an f of something, that means it's an x value.
Right, so this is the input value that you would put into F to get that Y value, correct? So C's got to be its value, correct?
Yeah.
Okay, super. All right, here we go. Ready, Caleb? We're going to use, so this is the intermediate value theorem. It's basically saying this is a low Y value. This is a high Y value. If I'm going from this low Y value to this high Y value, somewhere along the line, I'd had to go through K if you're continuous, right? So this is saying that's what the intermediate value theorem is saying. It says, use the intermediate value theorem to show that the polynomial, this polynomial, so this is going to be F. Okay, that's what F of X is. This right here has a 0 in the interval 0 to 1. Okay, now there's a lot of zeros in there, isn't there? There's 2 that I'm seeing. So I'm going to ask you these questions. First of all, what's A? 0. 1 for 1. What's B? 1. Perfect. What's F of A is going to be F of 0. Would you agree with that? Since you said A was 0? What is F of 0? Pardon? Oh, I got to make one quick, I understand why you're getting confused, and I'm going to make one quick adjustment, okay? Instead of plus, I'm going to make this minus, okay? So you're saying if I plug 0 in there, I get 1. I agree, okay? F of B, you said B is 1. And shoot it, there's something that's not. I'm going to make one more change. I'm going to make this a 3. Okay, there's a lot of things wrong with that function. Okay, so I'm going to make that a 3. So it's x cubed minus 3x plus 1. Okay, if I plug 1 in there, what do I get? I get -1. Okay, so if I would plot this, I'd have a point at 0, 1. There's 0, 1, correct? And right here, if I plug in 1, I get a -1, correct? And this thing is continuous, correct? Something like that. So that could be a drawing for this, perhaps. Okay. So what does it mean when it says, show that the polynomial function has a 0? What does that mean? Crosses the x-axis, correct? Because this 0 is a y value. This 0 is k. And I want it in between these 2 points, correct? So is 0 between 1 and a -1? Yeah. And the picture shows it, doesn't it? So show that the polynomial, I just showed it because how did I show it? I just plugged in my endpoints and I said, hey, this k value is between, which is a y value, is between these 2 y values, right? This 0 is between there. So I'm going to write my justification. which you are going to have to do a number of times. So I'm going to say f is continuous. Since f is a polynomial. And 0 is it between f of a and f of b. I think b gave us a -1 and a gave us a +1. So I got to put them in the right order. Caleb, would you agree with that? So there must be a c. Where's that c going to be? In 0 to 1. Take a look. It crosses the x-axis between 0 and 1, where f of c equals k. So what am I going to write for k? F of c is going to equal what? 0. So c comma 0 is my x-intercept, which I think, Caleb, you said. All right. Next page. This is from the 2000 AP Calculus test. It was number 3. They give you a chart. So here's your x values. You can ignore this because that doesn't make any sense to you at all. You can ignore this because that's not going to make any sense to you at all and you don't need it. It says the functions f and g are differentiable, which means you can take a derivative at every point, which does not make sense to you. And it says g is strictly increasing. If you notice, g is getting bigger. 2, 3, 4, 6. The table above gives the values of the functions and their first derivatives at the selected values of x. I crossed out the first derivatives. The function h is given by h of x equals f g of x minus 6. Explain why there must be an r in this interval such that h of r equals a -5. So, Sarah, what's a?
One.
1, perfect. What's b?
3.
Perfect. So I want to know, here it says h of r, I need to know h of 1. I need to know the y value. How will I figure that out? Do they tell me how to figure out h if I have a number?
It's f of g of x.
F of g of 1, right? Would you agree?
Yeah.
Minus 6.
Mm-hmm.
Can I figure out what g of 1 is?
It would be 2.
Perfect. F of 2 minus 6. Would you agree? Because you said g of 1 was 2, so I replaced it with a 2.
Mm-hmm.
F of 2.
9.
9. 9 minus 6 equals?
3.
Notice how 3 is just all over the place. H of 3, you would tell me would be f of g of 3 minus 6. What's g of 3, Sarah? G of 3, Sarah?
4.
4 minus 6. What's f of 4?
-1.
-1 minus 6. What's a -1 minus 6?
-7.
-7. Perfect. What's my K? It says, explain why there must be an R in 1 to 3 such that h of r equals a -5. What's my K? What's my other y value I need?
R.
R is an x value because it's between 1 and 3. And we plugged 1 and 3 into there. You're doing really good. What's my K? It's got to be a y value.
-5.
-5. Is -5 between 3 and a -7?
Yes.
Yeah. So if I start at the point 1 comma 3 and go to the point 3 comma -7, aren't I headed down?
Mm-hmm.
Don't I have to go through a negative? Won't I have to get a -5? So in other words, if I drew this graph, 1, 3 is up here. 3, -7's right here. Here's the interval 1, here's the interval 3. And I go down to here. Some here is a -5, correct?
Yeah.
Doesn't my R have to be there
Mm-hmm.
based on my beautiful graph? So it wants us to explain. So I'm going to say H is continuous. I always have to say it's continuous because it doesn't work if it's not continuous, right? Gabe, wouldn't you agree I drew that line without picking it up? It's got to be continuous. H is continuous. Now, you guys don't know this yet, but you will, since F and G are differentiable. And it doesn't make any sense, but you have to tell them why you know that. And -5 is between F H of 1 and H of 3. What should I write first, Sarah? H of 1 or H of 3? Which of these numbers, which of these y values is less than a -5? H of 1 or H of 3?
H of 3.
Perfect. So -5 is between H of 1 and H of 3. But I have to write this. So there must be an R, because they're talking about R and not C, in the interval 1 to 3, such that H of R equals a -5. Now, these are the last two things you write at the end, Sarah. By IVT, the intermediate value theorem, which says an intermediary. Have you guys ever heard of what's the story? Cyrano de Bergerac. You ever hear that story? Cyrano de Bergerac. Okay. All right. An intermediary is somebody that works between two people. The immediate value theorem says always gives you a y value that has to be between two y values. You have to figure out what those two y values are and then say, hey, I know it's there, one, because the thing's continuous. And here's the y values I'm comparing. They know what H of 3 is, the AP people, because you figured it out. You know what H of 1 is because you figured it out. And my special y value, which is K and -5, is between there. So that must mean there's a spot, an X value, a C, in this case they called it R, that it crosses between in that interval, between 1 and 3. It has to happen, doesn't it? That's what the intermediate value theorem says. So if you take a look at the handout, you'll see that's what's on here. And here's the example I give. It says, let f be a function, and here's a function. It's ugly. Show without using a calculator there exists at least one zero, so this is like the one Caleb did, right? This zero is the k value. It's the y value. It's saying, hey, it touches the x-axis within this interval. So this function crosses the x-axis between 0 and pi. This function is continuous on the interval, so the IVT must apply. So they plugged in 0. If I plug in 0 here, e to the 0 power is 1, so it's a negative 1, times the cosine of 0, which is 1. So they get negative 1. Then if you plug in pi, you get e to the pi. Well, you don't even need to know what that number is. You know that e is around 2 point something, right? So I'll use 2. Pi is around 3. I know it's bigger than 2 to the third, correct? Which is 8. So it goes from negative to positive, correct? I go from below the x-axis to above the x-axis. Do I have to cross the x-axis? Yeah. So here's what I wrote. F is continuous. And I said, you need this. You need to say it's continuous, and you need to say where it's continuous. Because I don't know if it's continuous anywhere else. I know they tell me it's continuous from 0 to pi. F of 0 equals a negative 1, and f of pi equals e to the pi, which means 0 is between those two numbers, those two y values. So there exists a c in that interval where f of c equals 0 by IVT. That's the form you have to write it out. And that's where I'm going to stop because you guys are tired and I've talked way too much. So I'm going to let you guys in the abyss go have something to eat. And we will see you tomorrow.
Hey, Mr. Kruger.
Yes.
I was wondering, what does QED mean?
Quite easily done.
Okay, thanks. I just didn't catch that.
It doesn't really mean that, but that's what I use. It's actually Latin, and I can give you the Latin tomorrow. It means what was to be demonstrated has been done. And every mathematician, when they do a proof, ends their proof with QED.
Okay, thanks.
Okay.